Okay, good morning. It is 11 a.m. Eastern Time. Welcome to today's round of MGIS capstone presentations for the Spring 2 term of 2022. I'm Jim Detweiler, the faculty lead for the Geospatial Programming Certificate. For those who don't know me, we have 6 presentations scheduled for today. A few reminders. Presenters, you're going to have 25 minutes to give your talk, followed by 5 minutes of questions. In the audience, if you have a question for a presenter, please enter it into the chat box. You might also consider typing your question in a separate text editor and pasting it into the chat box when the presenter wraps up, so you don't distract them during their talk. Presenters, please read the question out loud so that anybody watching the recording will know what you're responding to. So without further ado, let's get to our first presenter, who is Andrew Shobe, who's going to talk to us about change detection of human activity through processing of remote sensing images. Andrew, are you ready to go?
I am. Just one quick question. I thought it was 15 minutes and 5 minutes of questions for this part based on the schedule. I just didn't want to overrun.
Okay, well, if that's what you were told, then I will not force you to go an extra 10 minutes. So
I just don't want to run over anybody else. It looks like somebody starts at 11.
Yeah, you're right. My fault.
Okay, let me bring mine up. I'm going to share my screen. Let's go. Okay, are we sharing? I apologize. Doesn't seem to be sharing.
You should have the ability to do it. I've made that setting.
So,
should be in the bottom middle of your screen.
I see it's asking me to do something else. My apologies. Hold on.
We could move on to the second presenter if you. Is that okay?
Yeah, that's fine. I apologize.
Kyle, are you ready to go?
I'll yeah, I'm happy to jump in if that works.
Yeah, okay, let's do that, Andrew. Kyle, why don't you try to share your screen?
Yeah.
All right, looks like it's coming through. Yep, there we go.
Great. Okay, thanks. I'm Kyle, and my project is a methodology and Python software package for evaluating routability of road networks. Oh, let me turn my video on as well. Is that usually preferred for these?
You're welcome to do that, sure.
There we go. Great. So the question I set out to answer is, how can the routability of a featured dataset road network be efficiently and effectively assessed? Specifically, attributes like the size and weight restrictions, speed limits, anything which can cause a route to not be viable for a vehicle. So in my work as a defense contractor, I've seen that road network data sets are consistently incomplete when it comes to accurate routing, and it's an endless effort for the military to fill these gaps in their data. So there are many tools out there for validating the geometry and topology of road networks, but not so much when it comes to attribution. So given the relative difficulty of validation, there's sometimes an inherent assumption that the existing data is sufficient for generating routes, which may often be the case, but the outcomes can be very regrettable when the route is not viable. So here we have a rental truck, which was overly optimistic about fitting under this bridge. And here's a military convoy vehicle, which got stuck. So there's, of course, a lot of interest in making sure this kind of thing doesn't happen. So I proposed to develop a script to identify and evaluate key routing attributes in a data set. and check each feature. So it would attempt to locate routing attributes in the data set and check each feature to see which attributes are populated. Then it would generate a report of completeness metrics, as well as output shapefiles corresponding to each attribute, containing the geometries of the features with missing values. So this is, of course, only a partial solution to the larger problem, but would at least enable better evaluation of current data holdings. So the first goal of the project was to develop this script, and the second was to do a case study by evaluating sample data sets, both as a proof of concept and to be able to comment on the strengths and weaknesses of available data sources. So one of the foundational works in this area, referred to as Dijkstra's algorithm, proposed the pathfinding solution, which is at the heart of the vehicle routing problem for scenarios such as delivery driver route optimization. Much of the work based on Dijkstra is principally mathematical, but some of the more recent studies do include consideration of real-world routing constraints such as surface type, turn restrictions, and speed limits. Peter Keenan's Modeling Vehicle Routing in GIS is one of the few works that heavily emphasized attention to path constraints, as well as the need for complete and accurate data to leverage them effectively. So where is real-world vehicle routing with these types of restrictions actually being done? Well, commercial trucking companies and military organizations are two big ones, but neither is motivated to make their data and research publicly available. We do see work being done for oversized and overweight vehicle routing on behalf of state permitting agencies, but they don't tend to have the same resources as these other parties. So moving into the data, my methods here, these were the data sources I initially acquired. It's a mix of open sources, which are easier to access, but less attribute rich, and proprietary sources, which have more routing restriction information, but limited availability. And here's what I found on digging into them. So the OSM has a few routing attributes, such as speed limits and one-way directionality populated, but very rarely has any restrictions associated with bridges or tunnels. The Tiger line data was previously loaded into OSM and doesn't add anything for this purpose. The Utah AGRC data was also limited to basic road attributes. The ArcGIS street map sample was of good quality, but it was meant for visual use and didn't allow for digging into the attribution in the way I needed to. And the Here map data sample was of their lower level data without routing restrictions. So none of these initial 5 sources really had sufficient routing attribution to evaluate. So to be able to move forward with coding the script, I decided to artificially modify an OSM data set by manually adding bridge and tunnel attributes. And here is that modified OSM data set over Washington, DC, with some of the added bridge attributions shown, including heights, widths, and load capacity. Later on in the project, I was able to acquire a sample of Precise's Street Pro Navigation Premium dataset over the Bay Area of California as an additional evaluation prospect. And this dataset includes a streets layer with key routing attributes of max height, max width, and max weight. However, this information is associated with each street segment with no distinction for bridges or tunnels. So to identify features with unpopulated routing attributes, I first needed to ascertain where those features are. So I opted to use OSM as the basis for identifying bridge and tunnel locations, given its wide availability and clear indication of where those features are located. So I wrote a supplemental script to transfer restriction attribution over to OSM features based solely on proximity. So while this is a crude approach to data conflation by relying solely on the proximity to determine feature matches without accounting for size, orientation, attribute similarity, et cetera, it effectively provides a best case representation of the existing data. So I ran this proximity attribute transfer script to populate OSM features with the attribute values from the Precisely Street Pro Navigation Premium data. And here's the outcome shown for the max weight attribute as an example. So in this left image here, I have all of the OSM bridges in the sample area highlighted in blue. There are about 1,500 of them. On the right, this is all the Precisely segments which had populated max weight values. There are almost 80,000 of them. And finally, looking at the OSM bridges, which received a max weight value from the script, there were 516 of them. That comes to less than 1% of the precisely values accounted for, but over a third of the total OSM bridges, so not bad. So that was my main data. And now moving back over to the script development, this was my original concept diagram for the script. So starting with an input data set, I wanted to identify routing attributes using regular expressions. I hope that by using a few different sources with different structures to design the tool, I could build in flexibility to support other similar schemas as well with some assistance from the user. Then evaluate the data set by building an attribute dictionary and report the outputs. So a large portion of this diagram was devoted toward making the tool smart. I was excited and had a vision for how to achieve that, but the variation in data schemas turned out to just be beyond my skill to handle within the project scope. So I ended up moving to a model effectively more like this, where the routing attributes are passed directly into the script as an input. I tried to make the user friendly still by providing the list of fields to select from in the tool interface based on the input feature class, which I accomplished using the update parameters method within the tool validator class for the script, which was neat to learn how to work with. So a brief tour of the Python script, which I wrote to focus on an OSM-like data structure to match my doctored sample data. So I used a class structure to store and process all the information for each data set. I used search cursors to iterate through the features in each feature class to build dictionaries of the attribute values. And then I used the dictionaries to report the most common values and the features with no value populated. And then to achieve a spatial output, I created a shapefile corresponding to each attribute of each feature class and added the geometries of features missing route attribute values to the corresponding shapefile. Okay, so moving on to results, starting with the artificially modified OSM dataset to which I had added routing attributes. The light blue selection here shows all of the bridges and tunnels flagged as missing one or more of the identified attribute values. And so it flagged a lot of features, but is this useful? It gives us some overall perspective as to what extent and where the data set is incomplete, but the output is overwhelming, I think. So, okay, then what if we add an option to limit the analysis to a single route? So I generated sample routes using Esri Network Analyst and fed them into the attribute evaluation script to use as an input for location querying. So the resulting output now is easier to interpret and apply as it represents just the features along the identified route for which there is insufficient restriction attribution. Now returning to the real data, we're looking at the Bay Area data set of the OSM combined with precisely navigation premium attribution. And so starting with the roads, everything shown in pink here is a line segment missing a value. So for the max speed attribute, you've got 4,780 missing values out of 105,000 road segments. For one way, we have nothing missing. And for bridges, out of 1,489 features, we have 1,405 without max height values, 973 without max weight values. We don't have any with max, we don't have any max width values. And for tunnels, we have 384 out of 397 without max height. We don't have any max width values. So even with leveraging the precisely attribution, we have relatively few populated values here, and the features lacking information are evenly distributed across the sample area. So let's consider a route again to focus the evaluation. So I'm going to show line segments with unpopulated values in yellow, with a close-up to show that some of these locations contain multiple flagged features in close proximity. So we're flagging 29 bridges out of 32 without max height values, 25 bridges without max weight values, 32 bridges without max width values, 3 road segments without max speed values, and 1 tunnel without a max width value. For the road one way and tunnel max height attributes, we didn't have any values report as unpopulated. So here's a summary of all the results from the evaluate attribute script. The OSM modified data values just reflect the amount of attribute population I added for testing. But the two columns of OSM with precisely on the right are describing real proprietary routing data. Okay, so we've generated all that information. Now, how do we interpret it? So on the simplest level, it's acting as a guide for where we need additional data to best support routing. However, not every attribute can be interpreted the same way. For example, there's a difference in an unpopulated bridge max height value where there might not be any height restriction versus a tunnel max height value. So with that in mind, how can these outputs best be applied? So I think a likely scenario is to use this to focus in on one or two attributes that are most relevant for the use case. So for a tractor trailer, for example, the vertical clearance is likely to be most restrictive. On the other hand, if you're transporting a wide load, the max width becomes essential to understand. And then finally, why is the attribution from this premium navigation data set not more complete? So I suspect it may come down to how they organize and use their data and what assumptions they make about the parameters of roads, bridges, and tunnels along major routes, but I don't have a definitive answer. So where does this leave us? So we have a functional script for identifying features in the data, missing information needed for a reliable route analysis, as well as a spatial output, which can be used to visualize data gaps and target data acquisition, and a supplemental capability to transfer attribution to OSM geometry as a workaround for data in other schemas. While I've limited this evaluation to 2 data sets, adding others is straightforward, and these scripts can work anywhere the data are available. So for limitations, the user has to start off with a good understanding of what is in the data to pull out and use the appropriate attribution. Script also requires high quality data to be useful. If there's a total lack of routing attribution, we don't need the script to tell us where we are missing values. And finally, we don't have a way to distinguish features with truly missing values from those where the attribute may not apply, such as a max height associated with an open bridge. So one idea to overcome that last obstacle is to use supplemental data such as imagery to inform the analysis. A few additional ideas for future work. I think it'd be interesting to expand the support for schema types. This is currently geared toward OpenStreetMap. I could also see using the road category, for example, highway, secondary, local, etc., to either prioritize missing attributes or filter them by assuming major roads are navigable except under extenuating circumstances. And lastly, I think it could be interesting to generate a risk factor or confidence rating for a route or potential restriction instead of just a yes, no on whether it has the ideal information populated. That brings me to my lessons learned. First off, so I correctly anticipated the challenges associated with both the variation in schemas and the lack of non-proprietary high quality routing data. I needed to have a more thoroughly vetted approach in place for overcoming or avoiding those difficulties to allow for a smoother path to completing the project. Next, I had a concept of the range of the data structures I was likely to encounter, but I soon realized I had underestimated the differences and that building in flexibility to handle all of them was a huge task. And lastly, there was universally even less routing attribution than I expected to find on both the open source and proprietary side. And here are my references for the presentation. Thank you, and I will gladly take any questions.
All right, thanks very much, Kyle.
Thanks.
Questions for Kyle? Looks like you've got one in the chat box there.
Oh, chat box. Let me pull that up. Regarding the low-level routing attribution, I imagine that data providers would respond to customer needs. To help assess the need, wouldn't it be a relatively straightforward task to associate relevant traffic accidents with attribution gaps? Yeah, I think that's definitely a viable approach. That traffic accidents could be associated with routing attribution gaps. I think part of the challenge of this is that, I mean, the existing routing attribution is pretty good for sedans and just for car travel. And this is really geared more towards either tractor trailers, military vehicles, vehicles that are likely to push the boundaries of the heights, widths, load capacity, sharp turns, things that we normally sort of take for granted with our driving routes. So maybe pinpointing this traffic information for that specific class of vehicles could help get at some of that information. Thanks. Thank you. Any
another
other
one.
questions? Oh, great.
Another one from Ryan Baxter.
Great. Sounds like your script skillfully illustrates how incomplete the OSM database is. What do you think this says about OSM and its utility for purposes like routing? Should anyone ever use OSM? Yeah, I think I've been thinking about this with the incompleteness, and I think it kind of comes down to, it's easy, especially with a crowdsourced data set, to add in something, a road is here, here's the rough geometry, and maybe some basic information about it. But if you actually want to get at, what's the weight capacity of this bridge, and unless that information's there on a sign, you're going to have to do some kind of engineering study or something to get at that level of information. So for me, what that says about its utility for purposes like routing is that it's okay, again, for driving a car, you can probably just make some assumptions that those features are safe to drive on. But if you're talking about the military and they're moving equipment and doing this routing, which is the kind of questions that I'm looking at on my work side, it's not reliable, because you don't know where those potential issues are that could lead to those trucks getting stuck under a bridge.
Okay, well, thanks very
Thank
much,
you.
Kyle. Nicely done.
Thank you.
And so next, Andrew, you want to give it another shot?
Yeah, absolutely. I think it's working this time. I had to get out of it and get back in to make it work. But let's see.
Okay, Kyle, can you stop sharing first, and then we'll have Andrew share?
Yes, stop share. Thank you.
All right, I can see it now, Andrew.
Perfect. Get back up to the top. All right. So hi again. My name is Andrew Shobe. Capstone presentation, as mentioned, was automatic change detection of human activity through algorithmic processing of remote sensed images. And here's an overview. We'll go through the problem and hypothesis, data, challenges with that data, and some of the algorithms and approaches that were evaluated, results, conclusions, and references. There's a lot of ground to cover, so I will try to get through it quickly and save some time for questions. So the hypothesis that we brought forward from previous, it was based on the amount of capability and increasing capability in remote sensing that's available commercially and publicly in terms of both amount, resolution, numbers of bands available. Really getting a good capability, a good time to not only look at and process images to determine human activity within that particular image, but look at a series of images that can hopefully all be at the same parameters, and then be able to determine how much change is happening over time, and how this might be useful. You might say, well, I can probably do that through other means, permits and stuff like that. There's, much of the world, governments aren't structured to organize and gather that amount of data. And so it would possibly be available through remote sensing and processing, then giving folks tools to use. So, the hypothesis is we can do that and then follow the process of development, really, where land is cleared, you get roads, dwellings showing up, and then businesses, and then usually government structures later after they figure out that that they need them for increases in population. And so you can see that our objective is to quantify human growth activity in a region based on the structures, and then apply a process that looks at supporting analysis of urban growth for planning. And then as we developed, one of the risks I identified that I wanted to make sure was addressed was whether it was scalable or not, because we're going to look at a small section and to work on the algorithm. And then obviously some governmental agencies are interested in a little bit larger than potentially we or that I had analyzed. So data-wise, my criteria for the type of data I was looking for was multispectral, because I wanted to be able to not just look in the red, green, blue bands, but have at least near IR available, so that we could do some calculations and look at indices. And I'll show you more of those examples in a little bit. And I was excluding LiDAR data, just looking at imagery. The intent was to find meter or less, so sub-meter resolution that would allow for feature extraction. And many of the publications that are referenced later suggested at least a meter or less resolution to be able to do that. And then there was no funding for this, so publicly available would have been best. I know that there are other means, but I went with public, and that gave us gave me the opportunity to use the NAEP through Google Earth Engine in this case, because we could run both the algorithms and against available data that's there. It's 1 meter, 4 bands in much of the later images. So red, green, blue, and near IR, and it's free. So 2 cases of recent growth that I looked at, and then I kind of explored some others through the project, looking at Howard County, Maryland, Suffolk, Virginia, which both, as you can see here, my advance, those areas had reasonable growth over the period in the last decade, and I'm familiar with both of those areas, having lived in them, so could attest to their growth. So challenges, of course, sensor type is kind of a challenge. As it scrolls through here, through these images, hopefully it's coming through, you can see the buildup, but you probably also notice light intensity. All of those things are varying between all the images, which impacts the ability to analyze from image to image in a consistent way, so that you can pick out features. So without having to just do every image individually. So sensor type, it has some play in there. Also, the time of day and the season, which I'll talk to more in a little bit, affects that lighting that changes the shadow or changes the intensity of the values of each of the images, which hopefully some of the normalized algorithms can pull out those differences, but not in all cases. Season has some effect, and land use. So you can imagine, in the near IR on a hot day, hot roof, you're going to get a high value, but also in the winter, I found people with poor insulation, I was getting high values from late fall images. And I'm just speculating that same roof type, they just may have run their heater, which could impact the collection and the processing. So, and then land use, it said, hey, a bare field was going to be, an indication that we're going to move on to maybe the next phase. Well, also, depending on the time of year, could indicate that we just plowed over a field. So consistent time of year for the images was also of use in order to compare them and have values that was useful. And then finally, water, it does impact, and we want to minimize the amount of impacts from water as much as possible, particularly in the tidal regions around Suffolk. That was challenging for the algorithms. So on to the general approach that was to look at each epoch, each image, pre-process those, extract buildings, and then look at the changes over the course of those. So there are a number of methods that were available to do that. Initially, looking at clustering algorithms, so machine learning algorithms, many of which are available through Google Earth Engine. I used both a k-means and an x-means, and varied the intensity, or varied the parameters across each of the images within a collection in Google Earth Engine. However, it became really time and labor intensive to train the algorithm to look across all of those based on the changing in the values. And so I was really digging deep into each of the algorithms to determine why it wasn't scoring each image the same way. You know, the same tree in each image wasn't necessarily being classified the same way. So I dropped that and then started looking at also convolutional neural networks, which were available as an option. And there were many examples in the literature that I read on feature extraction using pulling out buildings and roads, and use some of MATLAB tools to look at initially those images. But again, tuning those became a little bit problematic, and it's a bit of a black box. So it was a little bit harder to determine why I wasn't getting the results I was looking for. So through all that experimentation, though, I started to notice a lot of patterns, and so my final algorithm that I ended up running was more of a manual inspection that and then I would then run automatic classification afterwards. So how did that work? Well, I looked across and kind of made myself a chart that looked a lot like this one in my notebook, looking across all the image bands at each of the types of areas that I was looking at, from wooded, field, or bare earth, in this case, asphalt for roofs and for roads, and then for the large part, or concrete, and then water and shadow, and started to look across that and the calculated bands to see where we might have the ability to discern just based off of a few calculated things and create basically a simple algorithm of classification. So NDVI, so vegetation index normalized, was a good way to classify many of the top types that I was meaning to look at. So moving 2 columns from there to DWI water index, it was helpful in picking out both water and shadow to a certain extent. And then I had read also about a buildup index in some of the literature where they were comparing shortwave IR and the near IR to pull out buildings. And unfortunately, since shortwave IR wasn't available band, I was able to compare it to saturation values, which in another in some of the literature, another study, they use something similar instead of shortwave IR band, and so I was able to kind of create my own buildup index that I was able to use as well in the algorithm. And then finally, saturation and value were used in one of the studies to break things out. So I looked at both of those using RGB to HSV tool, and found that I could find each of these elements and then run classification based off of calculating each band and then subtracting it out. So what's the algorithm look like then? Based on that chart, first intent was to remove shadow and water, which tended to conflict with the values that were human activity, and so I just eliminated those. And generally, it didn't largely affect. It was only a small percentage overall, but would have had a large impact on the values for the human activity. So I just cut those. Now, finding that those values used Jenks breaks, I found that using 5, 6, or 7 breaks and then finding the optimal one, I was able to find the values for the vegetation index that I could then go back and use to calculate what was shadow and water and eliminate those, or what was shadow, sorry. And then water was largely water index. So then classify the field and bare earth based off of the vegetation index, and then the remainder was human activity likely. I did a little visual inspection to make sure that it was pretty close. And then, so it sounds pretty manual, and it kind of was as I went through and developed the algorithm, but was able to automate all those parts using both largely Python. I looked at R packages as well, just to verify the Jenks breaks algorithm that was in Python, that I was borrowing from Python. I created a Python script that imported Earth Engine, ran through the Jenks breaks, and then calculated back out the values. So what's that look like as we get close here to the end? I'll play this. So this is the images from 2013 as it goes to 2017. Black was classified as human activity. Water and shadow are white. Green and is the bare field, and green is the fields and forests, and bare fields are in yellow. Calculating that, we did that for a 2x2 kilometer, so 4 million points at 1 meter resolution, and then compared the two from 2013 to 2017, and resulting in a 5% change in scene of human activity, a 30% increase in human activity based on that asphalt value. And you can see the amount of field going up. It was actually because the green grass filled in around the houses and showed it kind of followed that increase in there. I compared that to track estimates for that same area, which showed about a 30% increase in the number of households in the same period. A pretty close estimation. I don't have time to show you the results for Suffolk, but similar results there once I worked out how to get the tidal areas out of the calculations. So conclusions. So feel like we established that we can quantify the growth of human activity in a region based on the structures, do that automatically to support urban growth and planning. Is that second bullet a little speculative at this point, and the but I see an opportunity to be able to help in a bit larger scale, which was the third bullet. Is it scalable up to a certain level using Google Earth Engine? You have to be cognizant of the amount of points, but by breaking each block or tract into 2x2 kilometers was not hard to do, and then could evaluate each one and then bring the statistics back to using zonal statistics back to a larger piece of area. So that is scalable. And then although it's pretty rudimentary and kind of simple, what would be useful in future work if there was more time and available would be to refine that algorithm. I think the CNNs, the convolutional neural networks, have a real place here. It was just a little bit beyond my capability and scope for the time I had to work on the project. So with that, hopefully I haven't killed us too much on time, and I'll have open her up to questions.
All right, thanks, Andrew. Any questions for Andrew?
Okay, so quite an impressive study. You mentioned the effect of asphalt shingle roofing in your data. Given the increase in popularity of metal roofing material, do you think there would be a similar, similar effect from detecting this material? So I looked at both metal and tile, and so from a couple of studies, in the United States, the vast majority of stuff is asphalt shingle, although you're right, about 5% metal, I think, if I remember correctly in the study, roughly at single digits. And then, there were some metal roofs in there, and I was able to pull them out in this case by looking through those calculated bands. It was a small number, so it didn't have a large impact. Had I missed one or two, and which was the case, sometimes they showed up the shadow. But I was more concerned about looking at the southwest, where you don't have any asphalt; it's all tile. And so I ran a quick, look at Henderson in south of Las Vegas, where I was also familiar with there being a large amount of growth, and the algorithm would need some significant tuning to pull out because everything kind of looks the same there. And so that's where I think the CNNs would have more, if I could define edges and bring those and pop those out, I could use them to detect buildings in a better way than the simple algorithm. Hopefully that helps answer the question.
Okay, we have time for one more. Any other questions? Okay, well, nicely done, Andrew. Congratulations on finishing. And before we move on to the next presenter, I just want to ask the presenters to, in the chat box, if you would, when you're done, maybe put your email address in there so that anybody has any follow-up questions after the presentations, they can catch up with you. All right, that brings us to our next presenter, Jenna Sackler, who has she's going to talk to us about locating public restrooms in Washington, D.C. She's got a clever title. Jenna, are you all ready to go?
Yes, let me just get my screen shared. Okay, share. All right. Now where's the view slide? There we go. All right. Oh my gosh, why is this? Sorry, 1 second. There we go. All right. Hi, everyone. My name is Jenna Sackler, and for my capstone project, I decided to build a location-based services app to find restrooms in Washington, D.C., where I live. The genesis of this project actually came about because I love taking long walks or bike rides around DC, especially during the pandemic. And I don't always want to or have the money on hand to buy something from a Starbucks or other cafe to use their bathroom. And I generally knew where all the public restrooms were on the National Mall, although those are often closed anyway, so they're not always reliable. You're totally out of luck for other areas in the city. I started to look into this topic and I discovered there were so many more layers to the issue of public restroom access and being able to find public restrooms. So I decided that this was a great topic on which to apply the skills that I've learned throughout the MGIS program. This is a quick presentation roadmap where I'll quickly review the background, then dive into the app development process, walking through requirements definition, data gathering, and app design, and then finally discuss the limitations, opportunities, and lessons learned. I'll move through the next few slides of background pretty quickly because a lot of this was covered in my 596A presentation, so it may look familiar to some of you. So this screenshot shows the current public restroom situation in Washington, D.C., according to Google Maps. It is not ideal, although fairly typical for a major city in the United States. As you can see, there are plenty of public restrooms on the National Mall, which makes sense because that's sort of where the tourist population is concentrated in DC. But, outside of that, options are slim. There's a couple in Rock Creek Park and some other public parks, but otherwise nothing, or at least nothing that is easily captured on Google Maps. And as I said, this is pretty standard for the United States, but it stands in pretty stark contrast for many other major cities in the industrialized world. Now, as I mentioned in my introduction, there are many layers to the issue of public restroom access. In addition to convenience and support for tourists or people just out and about, anyone just out and about, there are real social justice issues at stake. The availability of safe, clean, and accessible public restrooms is vital to allow fuller participation in society for people with disabilities, unhoused people, people with other medical issues, women, and employees of industries where facilities access is not guaranteed. So understanding that social justice and accessibility side of public restrooms, in 2019, the DC City Council passed legislation to construct 2 additional public restrooms away from the National Mall as a pilot to hopefully add more later. Unfortunately, implementation of the plan was sidetracked by the COVID-19 pandemic, but in April of 2021, the DC Department of General Services picked it back up. And it is really exciting that DC is starting to wake up to this issue, but even then, as you saw on the Google Maps screenshot, you know, people need to be able to find the public restrooms in order to utilize them. So a location-based service
want to be seen, heard, known
is needed to locate them.
Obliged.
Sorry, is that my computer playing sound? Okay. So the American Restroom Association provides very thorough guidelines for designing public restroom locators, as you can see here on the slide. I'll first use these guidelines to evaluate some existing public restroom locators, and then at the end, I'll use them to evaluate my own location-based service that I create. So there's several public restroom locators functional around the world that hit all of the American Restroom Association's guidelines, but only 2 cover the United States. And only one of those is available on both the Android and Apple app stores. Flush, on the left-hand side of your screen, is available on both app stores and contains information for each toilet about accessibility and conditions for entry, meaning whether a key or code is necessary or if it costs money. Users can also update data for all of those categories. However, the black icons on the primarily gray base map can make it a bit, chaotic and difficult to discern the restrooms. Similarly, it doesn't list a facility's hours, and it does include private establishments. And it also doesn't immediately differentiate between locations such as parks, municipal buildings, or sites with portable restrooms. You don't really know what each of those icons is until you open it. Therefore, it doesn't meet all of the American Restroom Association criteria. Whereas public toilet on the right-hand side of your screen is only available on the Google Play Store. But as you can see in the screenshot, contains a lot more detailed information, and it also provides more filtering options. However, it also does not achieve all of the ARA's criteria because on the opposite to, in contrast to Flush, it almost exclusively features public restrooms and private businesses, missing several known restrooms in public parks or facilities. This slide shows the Great British Public Toilet Map. This web app fulfills pretty much all of the American Restroom Association criteria, and it really is an exemplar of a public restroom locator in terms of data, aesthetics, and ease of use. The only negative is that it's a web app rather than a native app, so users will need a good data or Wi-Fi connection to view it. Reviewing the pros and cons of the existing restroom locators was an important step for me for understanding what I do and don't need in my own app. After understanding the background, it was time to move to the actual development of my app. And the first step of that is to get at least a basic understanding of the customer's requirements. So my first step in defining those requirements was to conduct a user survey. I created a survey which had 7 questions on Google Forms. The three results shown here were the key questions in terms of actual functionality of the app. The other questions concerned the aesthetics of the app. I was able to get 50 responses in a 2-week period. The respondents varied in age from 19 to 72, but were pretty homogeneous in both race and socioeconomic status. This means I had to consider potential biases inherent in the answers and how that could impact my app development. For example, you see in the middle chart that 56% of respondents were usually able to locate a restroom when they're out and about. Well, if you consider that most of the respondents were white and middle to upper middle class, you might think about that group's general habits, such as traveling largely by car to specific destinations, or that they may have enough disposable funds on hand to purchase something in order to use a restroom. So those were just some of the things I had to take into account as I worked through my development process. And I tried to analyze some of those assumptions during my scenario writing exercise. Scenario creation is an exercise that allows app designers to understand why and how a user would interact with the product based on direct user research. I wrote 6 short scenarios, each about a paragraph. 3 were directly based on survey results and included a young professional training for a marathon, a tourist visiting family member in the city, and a DC government employee conducting field research. 3 were based on additional analysis and research into who may benefit most from public restroom access, including a construction worker, a taxi driver, and someone with a long walking or public transit commute. Writing these scenarios led me to better understand key features, potential aesthetic choices, to highlight those features, and conversely, some features that would be extraneous and detract from the user experience. After completing the substantive requirements definition portion, I began to formulate the functional requirements for building the app. The first step to guide my efforts was an entity relationship diagram, which is a way of modeling a relational database. It shows the different pieces of information that will comprise each restroom entry and how they relate to one another or are retrieved in the app. This is a fairly simple application. The only real function is to open the pop-up with the feature's attributes when selected. Therefore, the entity relationship diagram is also pretty simple and primarily shows the relationship between the various attributes and the primary point entry. Next, I put all of my requirements definition work together to create a wireframe prototype. This kind of low fidelity visual prototyping helps the designer adjust the look and feel of the application. In this wireframe, you can see the color scheme and simple features I intended to use for this application based on my research into some previous work on what design choices allow users to best interact with a location-based services app. And that was simple features, bright colors, not too much text, and some keynotes to understand what each feature means. Once I was satisfied with the wireframe prototype, I turned to designing the actual app. I had originally intended to build a native multi-platform app using ArcGIS App Studio. This promised to be an intuitive low-code software that would allow me to create custom apps publishable in both the iOS and Android app stores. However, when I investigated App Studio, it turned out to actually require a fair amount of coding, more than I was able to accomplish in the time constraints of this project. I also would have had to integrate the various application programming interfaces or APIs to truly customize the app, as none of the basic templates available on App Studio suited my needs. So I turned instead to ArcGIS Experience Builder, which lets you create web apps. And this, of course, means that it suffers the same display issues on mobile and necessity of stable connection as all web apps do. Experience Builder does provide desktop, tablet, and mobile shells that you can design your app in, so you can see how it will display in various size screens and try to account for some of those issues, but it's still not perfect. The next few slides show different views of the app in the desktop screen version versus the mobile screen version, and you can kind of see some of those issues in terms of the scale and display. So these are the desktop screenshots. And Experience Builder web apps are based on ArcGIS Online Maps. So I had to create that first and configure the pop-up and the symbology. I chose ArcGIS's basic restroom icon for symbology with bright colors signifying each type of bathroom. And you can see in the bottom left hand of your screen, there are notes on the help bar, which you can open by clicking the button to let you know what each what each color icon represents. For the pop-up, I had it display basic information such as name, address, type of facility, opening hours, and conditions for entry. One key feature that I'm probably the most proud of is that if you see where it says directions in the pop-up, I created a URL using Google Maps' developer documentation that, when clicked, redirects to Google Maps and shows walking directions from the user's location to the selected location using the phone or device's GPS or cell tower connection. And then these are similar screenshots on the mobile version, sort of gives you that comparison of how those display issues work. So when I reflected on the limitations of the insider leak, They coalesced into two different categories, technological and data. The two main technological limitations are that Experience Builders creates web apps, as I previously discussed, and second, that the edit feature is still in development. The edit feature is probably the most important feature after the navigation link, or even maybe more important than that, because without it, users can't fully interact with the app. This leads into the first of the data limitations as well. I was not able on my own to discover the opening hours conditions for entry for all 300 plus points in the app. The intention was that users would interact with the app to add that information for themselves to make sure it's updated and accurate. But with the edit feature still in development, they can't do that. My second data limitation is that, again, because of the time constraints, I was not able to do thorough field collection with ArcGIS Collector to identify all of the public portable restrooms throughout the city. I was only able to identify some of them. I instead, primarily for data, relied on Google Maps and Open Data DC, where I pulled shapefiles for entities that generally allow public restroom access. This included grocery stores, rec centers, public libraries, gas stations, and because of the Smithsonian Institution in DC, many museums all offer free entry. However, with the edit feature in once that's fully published, users will be able to add or update portable restrooms as they pass them in their travels throughout the city. So there are definitely, as you can see from the limitations, opportunities for me to continue developing the Insider Leak. First and foremost, depending on time, I could dig further into ArcGIS App Studio and actually create a native app. This would probably require at least a little bit of funding because even the basic license for App Studio costs money, and more comprehensive licenses obviously cost more. One opportunity to fund that is a grant hosted by the DC government Department of Small and Local Business Development to support the public restroom legislation. It provides funding to businesses that open their restrooms to the public, but may be worth contacting about the utility of the Insider Leak as a support element to that initiative. This grant was supposed to open in fall 2021, but as of April 2022, it had not yet been opened. So the Insider Leak meets many, but not all of the American Restroom Association's criteria for restroom locators. It differentiates between different types of facilities, allowing users to understand where those restrooms are. I also added the opening hours for almost all of the restrooms. When the edit widget is functional, users will be able to update conditions for entry for each restroom. However, it currently does not list portable restroom facilities, nor does it include all of the attributes that the American Restroom Association recommends. And these are also opportunities for development. I learned through this process the value of app development to the modern GIS practitioner, not least because my skills in that arena are not mature, so I was not able to create the app I originally intended. With smartphones becoming more and more ubiquitous, volunteer geographic information has risen in importance and allowed people to better map their surroundings, leading in turn to heightened visibility and perhaps even better distribution of resources. However, to take advantage of this phenomenon, you need a functioning app that takes user input and returns the right data. Thus, app development skills are key. This process also reinforced to me the value of agile project management methodology. Constant contact with stakeholders, which in my case was my advisor and a sample of potential users, during short sprints to achieve small milestones, allowed me to respond to changing requirements or the realities of novice app development. For example, upon discovery that I couldn't use ArcGIS App Studio to achieve my goals in the given time frame, I was able to pivot to Experience Builder. Through at least 5 or 6 iterations of design and comment, I was able to adjust the web app to ensure I protected the most important functions while adjusting the aesthetics to improve user interaction with the app. Finally, working through this process reinforced the very need for a public restroom locator in DC. While DC is making some slight progress on the issue of publicly available restrooms, as I mentioned at the beginning, their utility is limited if people can't find them or know they exist. This app, especially once developed into its full form, can help solve that problem. Thank you, and I welcome any questions.
All right, thank you, Jenna. Nicely done. Questions for Jenna?
This is a terrific application. Thank you for the excellent talk. I was looking at your prototype map and wondered if you had thought about any accessibility issues for the map itself. I'm thinking about people with issues seeing color, etc. That's a fantastic question and a really great point. Adjusting the map or adjusting the app for people who have issues seeing color or other visibility issues, I think is a pretty big challenge, and one that I would definitely need to seriously think about as I continue to develop the app. I think that maybe some that's definitely something that I need to think about. I don't know if there are some tools or functions to enable better screen reading and other ways to differentiate the different points for users who might have visibility challenges. I think those are available, and I would need to look into how to integrate some of those functions into the full app. But definitely something to keep in mind, especially since accessibility is one of the key reasons for creating this app. Okay, next question. Interesting project. Perhaps you already mentioned, but did you go back and ask potential users to use the app you created? What did they think about it? I did, and they really enjoyed it. Obviously, because it's a web app, there were some issues with display and being able to click all the buttons well on a mobile screen, much smaller. Every button was smaller. And then needing that stable connection, not being able to use it offline. But it was well appreciated. I have a friend who works in personal security and sort of is out in the city at all hours of the night. And he said he and his team certainly appreciated being able to look that up. So hopefully as I continue to develop it, I'll adjust some of those usage issues that users continue to point out on mobile screens.
Okay. I just have a quick comment, and that is that the Esri's JavaScript API includes an editor widget that if you wanted to revisit this using their API, it might provide the sort of ability to allow the user to submit their own data. So you might look into that.
Yeah, absolutely. I think if I were able, and hopefully in the future I will be able to look into ArcGIS App Studio, I'd be able to use the various Esri APIs to sort of integrate some of those widgets that are actually fully in function. It's just for the Experience Builder web apps, it's not quite there yet. So Hopefully the next version will definitely include that.
Yeah, no, what you've done here is a great step forward. Nice job.
Thank you.
All right, that brings us to our next presenter, Skylar Barlow.
Hi.
Skylar, are you all set?
Yes, all set, I believe. Great presentation, Jenna. Yeah, I would have been a key user of your app. I was caught dropping my bike and running through the portrait gallery more than a couple of times, so I appreciate that. All right, and just let me know when you see it, and we're good to go.
There we go.
All right, great. Hi, everybody. My name is Sky Barlow, and my presentation titled "The Landscape of Modern Slavery: Strategic Partnerships to Combat Forced Labor with GIS and Machine Learning." The project over the course of my capstone took several changes and evolutions in the methodology. So I'm going to show some of the ways that it's changed, and my project will actually continue past this as we develop this methodology more and continue to present and everything else. But we have preliminary results that we're excited to present on. So to give a basic background refresher on my projects, we're looking at cobalt and artisanal mining in the Democratic Republic of Congo. Cobalt being a mineral that's ubiquitous in modern electronics and in cell phone batteries and laptop batteries, and with the massive growth in the electric vehicle market, it's used in the batteries in those. So it continues to be widely used, and about 85% of the global cobalt supply comes from this little area within the DRC that you can see in the blue in the map. It is the copper belt. It's about 90,000 square kilometers and holds most of the global supply of cobalt. So the manners of mining cobalt, there's two main divisions. They have large scale mining. These are big operations by huge organizations with very capital intensive, with trucks and drilling equipment and huge workforces and lots of big interest that's involved in it. That accounts for about 70 to 85% of mining output within the region. But what my project is focused on is the artisanal and small scale mining, which sometimes can be as little as hand dug pits by one person. And within the Congo, this accounts for about 14 to 17% of all livelihoods. The measurement of this is a little fuzzy, as many times people digging holes by themselves will take their cobalt and sell it to large scale mining operations. So you don't really get to capture the exact number of how large the industry is. So this difficulty in measuring, this also brings results in forced labor and people looking to exploit people to dig these pits. There's a number of reasons or factors in this. Some is physical insecurity, where there will be an armed group, a militia that takes control of mining operations following a large-scale organization, debt bondage, and human trafficking, people being bought and sold and stolen from their homes. As of 2019, there's an estimated 35,000 children that were enslaved in this region just in mining activities. So the objective of my project is to identify these small mining activities, these operations within the copper belts. They're very difficult to track with the cloud cover, with the jungle environments. Some of them are very remote and they're just very hard to find. I'm working with Maxar on this and an international anti-trafficking NGO. We have become a Maxar purpose partner. So we're one of their first rounds of NGO humanitarian partnership where that gives Maxar's resources to non-profit organizations in industries like this. So we're very happy with the preliminary results we've had so far, and the work will continue as we go. All right, the study area that we looked at, so as I had mentioned on the right, the copper belt in the blue, it's about 90,000 square kilometers. Maxar's Secure Watch imagery platform can task about 10,000 square kilometers at a time. So we had to change focus our study area to the green area. That comes out to just under 10,000 square kilometers, and it's tasked for imagery. Every time their satellites pass over, they're grabbing imagery of this area between Lubumbashi and Kolwezi. So I'll talk a bit about the original workflow and how this evolved into the results that we currently have. The original plan was to create a training package in ArcGIS using 30 previously identified mining sites that were perpetrators of forced labor. Taking these sites, we mensurated the images into a shapefile, as you see on the right, with key features brought out like lakes, trucks, equipment, housing, fences, just anything that would assist a machine learning package in determining the key features. So using this, Maxar was able to run some supervised classification, and they're still continuing to run them now. But the real results came whenever they ran an unsupervised classification on the imagery, and going through all of the historical images that their satellites had collected in their repository. We were able to bring back some key results in that would have been totally missed otherwise. We noticed that in all of these mining sites, these orange tarps were popping up after large-scale mining activity had left. And looking through the literature with people that have been on the ground, there's been a couple instances where people mention the orange tarps, but there's no real study or connection to them. It was all just anecdotal. So we found these orange tarps would pop up and then leave. We assumed to cover individual digging pits. The tarps are very useful for us in that you can see them. They have a very unique spectral identity. And with this, we were able to create an multiple in-member spectral mixture analysis in R, able to differentiate between TARP and backgrounds. So we created a 0.65 threshold using mean zonal statistics for each band. So with these tarps, it made it pretty easy to identify them. We were able to pull out about 8 new sites just in the first round. So as we continue, we'll hopefully be finding more. And with this gives us a great baseline for further investigation on the ground. So as we find these sites, we'll be passing this along to our international anti-trafficking organization, who will work with local law enforcement to first determine the presence of forced labor or not, and take it from there. So we had some definite problems in the area, being the Congo. It's rainforest, so it is constant cloud cover. Finding images without clouds is really, really difficult. And with such a large study area, it just becomes even harder. The purpose partners with Maxar, this being the first rounds that they're working with organizations like ours, they're figuring out who has access to what resources, and some Maxar employees are giving their personal time to work on this. As we develop the results more and are actually able to present stuff like this, they've been excited. So we're hoping that it'll continue to grow as we go. But also there's no definite correlation with the orange tarps and artisanal mining. You can see in this bottom photo, they seem to pop up in towns also, and there's a lot of instances of them being in villages and not necessarily in mining operations, but there is a concentration that helps to identify mines if you're able to parse them out. So with this, we're going to continue our work, but we have some exciting first steps and things to present on. That is it for our presentation. That's where we are now. So thank you. I look forward to any questions, any comments you guys have.
All right, thanks, Sky. Questions for Sky?
All right. Congratulations, Sky, on this meaningful and consequential project. Do you have a guess about what the orange tarps are used for? Well, it's so rainy in the area, we can only guess. From working on the grounds, we know that rain and mudslides, and there's all kinds of things that will get into the pit. So there have been tons of records of cave-ins and people dying in this ASM activity. So people like to cover their pits up, especially during the rainy seasons. So that's our guess, just having to go from the imagery. That's what we have so far. Thank you. Anybody else?
Other questions for Sky? I'll ask a question. Do you have, you mentioned passing along findings to law enforcement. Do you have specific, have you had specific communications with any law enforcement along this line?
The organization that I'm working with has worked in other countries where, yes, throughout Asia and and Africa too, but the most recent ones in the Philippines and Indonesia, in India, there's lots of other countries that they've worked in, and it's very much we empower the local law enforcement to do things that they just don't have the resources to investigate. And this is our first foray into the DRC, so we'll be making those connections as we go. But we've been, I got connected through the capstone. I'm an unpaid researcher, so I'm just assisting as a geospatial analyst in all of this. But yeah, they've been doing this for over a couple decades.
Okay, and so when you say we, you're talking about Maxar?
Maxar, no, the international anti-trafficking organization that I'm working with.
Okay. All right, any other questions for Sky? All right, well, nicely done.
All right,
and
thank you.
congratulations on completing. And that's going to take us to our next presenter, Libby Duskin, who's going to talk to us about a web app that she's developed for zoos. Libby, are you all set?
Yes, I am. Can everyone hear me okay?
I can hear you great.
Okay, I'm going to go ahead and share my screen.
There it is.
All right. Okay. Well, thank you everyone for coming to my presentation on development and implementation of a web application to analyze geospatial data in zoological facilities. My name is Libby Duskin and my advisor is Professor Adrian Goldsberry. Just to get started, I wanted to quickly outline how this presentation is going to go. After the background and introduction, I'm going to discuss some of the previous behavioral studies and geospatial studies related to behavior, and then we'll discuss the web application that I built. I'm going to present the results and go through a case study, and we'll discuss some future work after that. So a little bit about my background and why I decided to kind of involve myself in the development of a web application was that I had previously worked on a study with sand tiger sharks, which is this guy right here. The study had aimed to understand behavioral patterns in relation to space use, which was done by manually recording their location and behaviors using a web application called Zoo Monitor, which I'll talk more about later. But we used it to create these heat maps, and we worked with several facilities to do this. But at this facility in particular was Epcot at Disney World. So zoological facilities can often be more than just a zoo. These facilities often contribute to research, rehabilitation, and conservation. More reputable facilities are often accredited by associations like the ones listed here, which have standards that facilities must meet and maintain, including regular monitoring of the animals and tracking of behaviors and movements. So why does animal behavior matter? Animal behavior is particularly important because changes or lack of changes can be indicative of needs or issues of an animal. An example is stereotypic behaviors like pacing, where an animal is walking back and forth in a certain area. These behaviors are important to track so that they can be monitored and addressed properly. So some previous behavioral studies and methods have been done with manual observations. One way this is done is by using an ethogram, which is created by defining behaviors that are categorized and are usually on a spreadsheet to record data and intervals. A lot of facilities now use ZooMonitor, which is a web application that allows you to customize an ethogram with buttons and different types of observations. Another method that some facilities have used is hormone data to see what an animal's hormones are doing in response to their environment. Some of the limitations of these types of studies is some facilities don't have the time or staffing to manually record data. There's also issues with interreliability between the users because what one person sees as an animal walking slow, another person might say is a medium-paced walk. So geospatial studies have been done at some zoological facilities. ZooMonitor has a feature that allows the upload of habitat images and integrates the manually entered data with an ethogram. Another method that we've seen a lot with wild animals to track movement or migration patterns is the use of GPS and accelerometers. These are now being used in studies at zoological facilities. They're often worn as collars or bracelets, as you can see here, depending on the type of animal. GPS collects location data and tells you where the animal is spending its time, and the accelerometers can measure motion or positioning of an animal. So these two methods combined can tell you a lot about what an animal is doing at a particular location over a long period of time. Some limitations of this is that these devices can cost a lot of money. GPS and accelerometers also don't track specific behaviors like an ethogram would. There's also an accessibility limitation to the analysis tools like ArcGIS Pro, and if the user who's collecting the data has the knowledge of how to do the analysis with that software, which is where my project comes in. So I have developed a web application using ArcGIS Online Web App Builder that would provide a GIS analysis tool for zoological facilities in a user-friendly format. So some of the objectives of this application would be to perform some functions like import geospatial data, draw a polygon of a habitat, clip the data to the habitat, perform an analysis, and calculate the distance between consecutive points. To do this, I partnered with Dr. Sharon Glazer at the Oregon Zoo to use their accelerometer data from a study on elephant recumbence, which just identifies when the animal is standing up or laying down. I also got a subset of their GPS data that was collected during a 4-year study at the Oregon Zoo when they were building a new habitat for their Asian elephants. And over here on the right, you can see some of the software that I used in this application development. So there were a lot of steps in order to get the web application built. First, I had to build an ArcGIS server using Amazon Web Services so I could host the web application, the custom tools, and the widgets on the Elastic Cloud Compute instance. Then I had to develop a Python script for a distance calculation code and bar charts. So the distance calculation code was intended to calculate the distance between two consecutive points so that users could further understand, how much an animal was moving in a day or between points and identify running versus walking. And a bar chart tool was done to kind of do an infographic summary of their data. And then I had to go into ArcGIS Arc Pro on my instance and configure and create the custom script tools and then publish them as a web tool on my ArcGIS Enterprise online portal. Then I configured a web application in ArcGIS Online Web App Builder with custom widgets I obtained and tools that I had configured. I then prepared the raw data that I got from Dr. Glazer in Microsoft Excel and imported it into the application. Now I can run the analysis in the application. So there are a lot of steps to using the application. So I'm going to go ahead and start with adding data. The Add Data widget allows you to add data from your ArcGIS Online account or a URL or a file upload if you don't have an account. So here I added a habitat polygon and the elephant GPS and accelerometer data, and this is what it looks like in the app. Now I can use the extract data tool in the analysis widget to clip the data to the habitat polygon. The output data format is a link that saves the result in a CSV file that you can add into the application, and this is what the output looks like. So you can see all the data points are now within the habitat polygon. If I didn't have a habitat polygon, we can actually draw it in using this custom widget that I obtained. This widget lets you export the drawing as a .json file and import it the next time you use the application. The draw widget that comes with the web app builder doesn't actually allow you to save drawings, so this was kind of the alternative. There's 3 additional analysis tools other than the extract data tool in the application. One of them is calculate density, which classifies point data from the most to least dense areas. It can be configured with what point layer you want to add an account field. There's some expanded options you can customize as well. And this is what the output kind of looks like. So you can see on this particular day, this elephant was spending a lot of time in the southeast area of the habitat. The Find Hotspots tool identifies statistically significant clustering of points. This tool allows you to pick a layer, find clusters of high and low using point counts or other features depending on your data, and define where the points are going to be possible, which I will define as the habitat polygon. There's some other expanded options, and then the output comes out as a link or a download, but is also automatically added to the layers in the application. The results show a map of hot spots and cold spots and their confidence levels of their significance. You can even click on certain points and see a kind of a breakdown of each point or view these in the attribute table. The Summarize Within tool gives you some custom summary reports using the habitat polygon as the boundary input and using the location data to summarize. You can pick counts of points by field and statistic. Here, I'm going to summarize the accelerometer data of standing up and laying down. And here we can kind of see that it doesn't give you a visual output, but it tells you the count of points. And then you can open the attribute table where you can see the count of points by category and the percentages of those occurrences. The distance calculation tool will allow you to input data as a URL or file upload, not by selecting layers in application. So we have to export the layers to CSV in the attribute table. And then in the distance calculation tool, I can select the file upload, and then I can input the name of my latitude and longitude headers. Then it gives you an output link, and you can click that link to download the output CSV file. And here you can see that it has calculated distance in kilometers and distance in meters between each consecutive point. I also wanted to have the users to have some kind of summary visualization, so I created a bar chart tool. This tool will allow you to upload the file similar to how we did in the distance calculation tool. You can pick the columns that you're going to be graphing for the X axis and the Y axis. You can customize the aggregation and titles for the axis and the graph. And then the output is a link to an SVG file. And here we can see this bar chart is a summary output of occurrences when the elephant was reported standing up, laying down, and the null values. Some additional tools available in the application are a base map gallery where you can switch out, where users can switch out base maps if there's something else they prefer. There's a share link to the app for different types of social media or email. It doesn't share the data, it just shares the link to the application. There's also an export widget option that allows you to configure a map layout. There's some advanced options to set some other configurations for your layout. And this is kind of an example layout of what it would look like. So you can see that there's a scale bar and a legend and a title. There is also a measurement tool that allows you to measure an area, distance, or point locations on a map, and you can customize the units of measurement if you would like. The attribute table widget allows for some filtering expressions, so you can select out certain data points if you want and export those results. So here in this example, I'm selecting for moments of the elephant laying down, and then it gives you, as you can see, 36 points that are instances of the animal just laying down. So there were a couple of limitations that I experienced when building this application. Some of these were file upload limits. Layer symbology cannot be changed in the application. There was some degradation with polygons that are added outside of an ArcGIS Online account. So you can see here on the right side that the ArcGIS Online file uploaded really well, and the file uploaded from the user's desktop as a shape file came out somewhat degraded. The bar chart summary was also limiting because what I had really wanted was an infographic summary that would dynamically change or update as the user moved around the application viewing their data. And adding data also required users to make their files publicly available to be able to be uploaded into the application. So this is what the resulting web application looks like. And as a whole, when you first access it, you can see the map window takes up the majority of the view and the widgets all frame it. And I intentionally have the widgets placed in flow of order of use. So from add data and then layers listed, and then the analysis tools, and then the calculation tools and drawings of the habitat polygon. So I actually ran a case study for my application, and I had my husband test this out with our dog. And my husband happens to work in an aquarium, so he understands a little bit about these types of studies. What we did was strap an iPhone on with a GPS application onto our dog and collect some data. He was able to import the data into an application and perform the analysis. He was able to clip the data to a backyard polygon that he drew, perform a hotspot analysis, which was pretty consistent with what he saw in real time. And he also did a density calculation, and he could see kind of the areas in particular that our dog was spending a lot of time in. So what he said he really liked about this is that the Summarize Within is a valuable tool to report daily activity. And the app is also great for identifying areas of high or low interest to the animal. And this would be great for things like identifying pacing. And he also said that this is great for big picture animal management. So if you're trying to inform a decision, it can be backed by a lot of visual and numerical data. What he didn't like about it was that the data files for importing can be a little bit confusing and the bar chart was limiting. He also said that while the app is very user-friendly, it can be a little bit confusing to use without some kind of guide if you're not entirely sure what all the functionalities of the app are. So in the future, I'd really like to refine the usability of the application. I would like to incorporate Survey 123 and 3D GIS, just so if users wanted to incorporate manual addition of data, they can using Survey 123, and 3D GIS is also really important for animals that use a 3D environment, such as birds, and being able to understand their space use. That also kind of brings me into aquarium usability. I had really wanted this app to be able to be used within aquariums as well. But finally, I'm going to present this web application to the Oregon Zoo since they let me use their data. And I really framed this application development around the results from their study. And I was trying to match what methods they used for analysis to inform the tools that I would have in my application. And finally, I just wanted to acknowledge the Oregon Zoo and Dr. Sharon Glazer and the Asian elephants who allowed me to use their data for my application testing and development, and my advisor, Professor Adrian Goldsberry, for guiding me and encouraging me through this capstone project, and Professors Jim Detweiler and Ryan Baxter for helping me create the script tools, troubleshoot the application, and develop the ArcGIS server. It was a lot of learning and many hours in front of a screen, but it was an incredible learning experience. So thank you so much for that. Here are my citations and any questions.
All right, thank you, Libby, for a very nice presentation. I really liked the visuals. That was awesome. Yeah, questions for Libby? I can kick things off. Libby, you needed to use ArcGIS Enterprise to implement some of the stuff that you wanted to do. How much of a barrier do you think that would be in getting this getting your app out to be used by facilities?
Yeah, so that was one of the other limitations. Of course, right now through Penn State, I had some credits for Amazon Web Services, but I think it charges you about 3 cents an hour to run the enterprise. So of course I have to stop the instance when it's not in use, which means that the application doesn't work if the instance isn't turned on. So that limits how accessible it can be at all hours of the day to people if they were to use it. So it's definitely a limitation. If there was some way to do some kind of sponsorship or something by someone who could afford to do that, because then it would be more available to people.
Right. Looks like you've got a question in the chat box.
Yes. So Ryan asked, great presentation. Perhaps you said this already, but had you considered using non-Esri or open source resources to develop this application? I did consider that. I didn't know enough about them or have enough experience with those other options to develop the application. I know when I had talked to Dr. Glazier, I thought about using QGIS to write the code for some of the script tools just because it would be more open source and publicly available, but I don't know about developing an app. Awesome project and great use of Prezi. What would be your advice to would-be users of Web App Builder? Be prepared to do a lot of Google searches. There's a lot of quirks to it. It's really great. Some of the widgets can be limiting and you have to figure out different ways to configure it. There's also a great community on the Esri community pages that post a lot of answers or ways to work around different things in the Web App Builder. I also know that there's Web App Builder for developers, which uses a lot more code, but it seems to be more flexible and can like customizable towards what you want to use.
All right. Any more questions for Libby? We still have a couple minutes if there are any. Okay. Looks like you're off the hook, Libby. Nice job. It was great to see this come together. As you said, Ryan and I helped a little bit behind the scenes, and just really nice to see what you were able to put together.
Yeah, it was awesome. Thank you so much again.
Yeah, great. All right, that brings us to our last presenter, Cassandra Pritchard, who's going to talk to us about migrating an Esri add-in from ArcMap to ArcGIS Pro.
Hello, everybody. Can you hear me all right?
Yep.
All right. So I'm going to go ahead and share my screen here. All right, so my name is Cassandra Pritchard. A little bit of background on me. I work as a GIS specialist and systems engineer for Kisters North America. Today, I will be talking about migrating an add-in, the Whiskey Arc extension, which I'm the product manager for, from ArcMap to ArcGIS Pro. Just a brief outline of what I will cover today. First, I'll tell you a little bit about the add-in and what it actually does. Then I'll discuss why it needed to be updated. I will also talk about some of the obstacles I encountered during this project. After that, I would like to give you a live demonstration of the add-in, and I will wrap up by going over some of the next steps for this project. The image here is just a screenshot of the add-in and some of the data that I pulled through for daily flow time series from one of my customer systems. So an overview of the add-in and what it actually does. The Whiskey Arc extension gives ArcGIS users access to time series data stored in the Whiskey database. Whiskey is used to store a variety of time series and environmental sample data. So we do everything from some customers have 1-minute sensors to half-hour sensors. We'll often download and integrate data from sources such as USGS. But you can kind of see there on the screen that this data can be graphed, tabled, lots of calculations run through it. The great benefit of this add-in is that once it's implemented in ArcGIS Pro, users can take this data and perform geospatial analysis in ArcGIS Pro. They can create map layouts to share with their organization. They can also publish data online to web maps. Our primary users are surface and groundwater monitoring groups, dam operators, people who do climate monitoring, also water quality sampling and ecological sampling. So you can see why it's valuable to analyze that data. So why do we need to update this? Two main reasons, really. The first is that users are migrating from ArcMap to ArcGIS Pro. There were also changes made to the software development kits used to develop the add-in. So the old add-in is not compatible with the new version. We did run into a few obstacles during the course of this project. As a business, we have a lot of projects going on, and some of them have to be prioritized over others, especially when we consider, budgeting and project management timelines. I also work with an international group of developers, which means we're rarely online at the same time, and some of us speak different languages. The developers I work with specifically are in Germany. So there's part of the year where I think there's an hour in the morning where it's the end of their day and the beginning of my day, but most of the year we are a bit separate. This mostly means that we have to find concise ways to communicate with each other. And on the left here is an example of a diagram I would put together to describe features that need to be developed in the add-in. You can see I keep it pretty simple and really focused on the imagery to get my point across. And then the last is something that most people need to be cautious about in their work these days. We had a system outage in the fall after a group tried to access our network. They attempted to launch a ransomware attack. I'm glad to say that they were not successful in that. As a result, I was offline for almost 6 weeks and unable to use my work laptop at that time. Also, the process of rebuilding our systems and bringing things back online has taken some time. And let's just say there was a period where I wasn't so sure I had much of a project left. Luckily, we were able to recover most of the work from a version I had stored on my personal laptop and get things moving again. And then next, I'd like to actually show you what this thing does. So if we go over here to ArcMap, first of all, adding it to the application is pretty simple. You just go to the add-in manager here and direct it to the folder location where the add-in.x file is located. Once it is implemented, get that out of my way. It shows up here, has its own ribbon here, and then it opens this side pane where you can access all the site stations in a very familiar view to what you would have in WSGI. So the basic hierarchy in WSGI is you've got your sites, and within your sites you have different stations. So, where you would have different river gauges or something like that. See if I can find underneath that. Typically, these must be water qualities. There we go. So you've got your sites, stations. Under there you have parameters. So this is just a flow parameter here. And underneath that you would have the different time series you have. Like I said, there's often the original data and then some calculated or edited time series that follow after that. And then once, you can also pull time series just by going to different groups. So in this image here, I have the daily flows for this time series group. So it'll pull data from all of here. If I right click and open this value layer, it will pull either the last value, most recent one, or I can set a time range of values. I won't click this right now because it takes a little while to load all of these, but I've already loaded data for the current water year. So if we go back to the contents pane, once I load that, I can see that right here and I can symbolize it. I can set the time layer on it. I can come over here and kind of see how things have gone for the season. It's just kind of fun. And another thing that we can do is, and this is part of the testing, is just go through different workflows and run things through Model Builder, publish things online, create different charts and graphs, really just utilize that data as much as possible. So if I go back here, we can just put this up a bit. So what are the next steps for this project? Currently, I've been working on a lot of testing, as I was just mentioning, running things through Model Builder. This is a model I built to calculate the current month daily flow and summarize those attributes, and just really going through different workflows. I work pretty closely with our customers and have identified a few that I would like to give the current version of the application, just so that I can get their feedback and make sure that there aren't any bugs or workflow issues that aren't apparent to me. And then finally, this really focuses on the time series side of WSGI. As I mentioned, there's also a water quality and ecology module. Those are more sample-based instead of time series-based, so the structure for them in the backend database is different. This application was originally developed for the time series side of things, so we're looking at adding new features to it now, especially as we get more and more customers in these areas. So once this is out and developed, it's a lot of seeking customer funding and support to further build this out and make it usable to more groups. And with that, I will leave you guys open for questions.
All right, thank you, Cassandra. Questions? I'll ask, what sorts of advice do you think you would give to someone going through a similar ArcMap to Pro migration? Lessons learned.
Really, and it applies to all projects, developing a roadmap and really making a list of the features that are important to carry over. One thing that I had to work on with my development team is they aren't ArcGIS users, so I'm really directing them on how things need to work. And part of that is just, they saw things like they wanted to build in a bunch of tools into the add-in, and I had to make it apparent to them that, really all of this is built into ArcGIS already, so it's better for us to take advantage of the tools that are already there. Another benefit to that is that as we go through different ArcGIS upgrades in the future, we're not constantly troubleshooting tools that we built ourselves. We're really just providing the data and feeding it in. So that was something I had to work on with them a little bit. And yeah, just really making sure that the list of features is there, that you've got backups of things everywhere. Yeah.
Okay, thank you. Other questions for Cassandra?
All right, it sounds like everybody's ready for lunch.
That might be.
I will go ahead and put my email in the chat here, and should anyone have any questions or want to check this out, feel free to shoot me a message.
Yeah, good. And the same goes for the other presenters. If you haven't yet shared your email address, please go ahead and do that in case anyone has any follow-up questions. Looks like David might have a question for you.
Looks a little bit more of a comment. Seems to me the lessons you learned would make a valuable case study in project management. I definitely agree there, especially when it comes to things like the, system outage that we had to go through, and really the strategies we used to work around that. Having such a great team, like I said, even though we're global, we work very well together, really made a huge difference and helped us get back on our feet pretty quick. But yeah, certainly. Yes, of course. All right, well then I will let you guys go unless you have anything else for me.
Any last questions? Okay, well, that's going to conclude our presentations for today. I want to congratulate all of our presenters for all of their hard work culminating in this presentation. Some of you may have some writing to do yet, I don't know, but at least this big milestone's been reached. And that's going to conclude today's session. And I wish everybody a good afternoon.